the house. Today, we're doing Math Analysis, Chapter 4, Section 4, Applications of Trigonometry. I'm your host, Dr. So now we're going to be doing trigonometric applications, which means word problems.
Just the facts, ma'am.
Okay. We're dealing with simple harmonic motion. So motion that goes up and down. Like if you think about a spring with a weight on the bottom, and you pull it down and then let go, and the spring's going to be bouncing up and down, there's your simple harmonic motion. Now, the other thing is if we have a string with a weight on the end, and we pull it up and then we let it go, and it's going to be going back and forth. So more simple harmonic motion. Around and around, like an engine. You see both the piston moving back and forth and the crankshaft moving around and around, or a Ferris wheel. All kinds of things are simple harmonic motion. Sound waves, which we're going to be talking about in a little bit when we talk about frequency. Okay, the equilibrium point is the midline of the graph. So if we think about the midline of the spring with the weight on it, it's right in the middle between the top and the bottom. So that's often going to be d equals 0 just by definition. The period is the length of time for one cycle. Now notice time is our x-axis now. So the length of time per cycle, or seconds per cycle. Now frequency is the reciprocal of period. So instead of seconds per cycle, frequency is cycles per second. And so frequency is 1 over period, which is, instead of 2 pi over b, it's b over 2 pi. Okay, now, we can get a little more sophisticated by making a vertical shift. Like if we have data that the middle of the data is not 0, well then you're going to have a vertical shift, a d value. Now, we're going to define that c equals 0. There is no horizontal shift because we basically start the function at t equals 0. So how do we get our equation? First thing, we need our d. So we find the midline by averaging the high and the low. High plus low divided by 2. So notice, I take the high, I take the low, I get the average. What do I have? Well, I have the midline. So that's my d value. Then I want the amplitude. Well, the amplitude is the distance from the midline up to the top, or the midline to the bottom. Well, so I go high minus low divided by 2. High minus low would give you the whole distance from top to bottom. If I cut that in half, then I have the amplitude. Now, last, I find b, which is the period. So period's 2 pi over b, which means b is 2 pi over the period. So that's pretty easy too. Okay, let's try a problem. We have a curve here, and we need to find the sinusoidal function that fits this curve. Now, if it started at the top and went middle, bottom, middle, top, then that would be a cosine curve. But we see it starts in the middle, top, middle, bottom, back to middle. So that's a sine curve. So we know what we're looking for then is going to be y equals a sine bt plus d. Now, first thing you can see is d equals 0. But let's do it by the numbers. The high value is 2. and the low value is -2. So the average between 2 and -2 is 0. So basically that's my D value right there, D equals 0. Now, the amplitude is going to be the high minus the low divided by 2, which is 4/2, which is 2. And I could see that just by looking at the graph anyway, because if I look from the x-axis up to the top, it's going to be 2. Now, the last thing I need is the b value, and so that's going to be 2 pi over the period, and the period we can see is 12. So that means my b is pi over 6. Okay, so I have everything I need then, is I go y equals a sine b t. Piece of cake. Okay, now let's crank up the juice just a bit. Why do I keep doing that? Let's crank up the juice just a bit. Okay, we'll just leave that mistake in there. Okay, so we have a high temperature of 75 degrees and a low temperature of 65 degrees within a 24-hour period. That sounds like typical Orange County summer weather. Nice. So, all my friends from Pittsburgh who are watching this video, it's way hotter where you are and you don't even like it. So, you should move out here. Okay, so we're trying to find the sinusoidal function that models the temperature in this day. So, first thing I look at is what's my amplitude. Well, oh, and incidentally, we're just going to define the function as sine. We could use cosine, but we'll just say that our function begins at the midline. So it's 70 degrees when we start our clock. Okay, what's our amplitude? Well, it's going to be high minus low divided by 2. Well, the high is 75, the low is 65. Divide that by 2, and you get 5 degrees amplitude, which makes sense. It's going from the midline of 70 up to the upper 75. That's 5 degrees amplitude. Now, your vertical shift is going to be high plus low divided by 2, which is 140 over 2, which is 70. So that's what we realize also, is that the midline is at 70 degrees. And now our period, well, our period is 24 hours. So the b is 2 pi over 24, which equals pi over 12. Now, so what we see then is we're starting the clock when it's 70 degrees. The upper temperature is 75. So within the first quarter of the day, it's at the upper temperature. And then the second quarter, it's back down to the midline. Third quarter, it's to the bottom line. And fourth quarter, it's back to where it was at the beginning. So here's our curve. So notice what's happening. It starts at 70 degrees and the temperature increases. At first it increases quickly, but then it slows up as it gets to the maximum temperature. Now it stays at the top temperature for a little while and then it slowly begins to decrease. Now it's decreasing faster as we get down toward the lower temperature. Now when we get really close to the low temperature, it slows down again, so it stays toward the lower temperature for a few hours and then back up to the midline. So there's our curve, there's all the characteristics. So that makes our equation y equals a, which is 5, times sine of bt, pi over 12, times t. And remember, in this case, t is time, plus the midline of 70. That's it, game over. So basically, if you know what time it's 70 degrees, that becomes t equals 0, and then you could find out what temperature it is any other time in the day. Okay. Here's an example straight from the book. It's on page 183, and it's example 4. We've got a certain animal population that can be modeled by a cosine function. So here it is. Population as a function of time equals 1200 times cosine of pi over 5t plus 9000. So p is population and t is in years. So first we find the period. So period is going to be pi over 5, or it's 2 pi divided by pi over 5. Which equals 2 pi times 5 over pi, which equals 10 years. So there's our period, is 10 years. Okay. Next, we want to find the maximum and the minimum populations. So that basically says, first of all, where's the midline? Well, that's going to be where, now you know what, for cosine, that's not going to be as easy. Sine, the midline would be where t equals 0. But, okay, what we know here is A is 1200 and D is 9000. So what we know is that A equals max minus min divided by 2, and D is the average of the max and the min. So what we have here then is max minus min, max minus min equals 2400. And here we have max plus min equals 18,000. Notice all I did was multiply 2 on both sides here, multiplied 2 on both sides here. So I have two equations with two variables. If I just line them up, notice I have max plus min equals 18,000, and then max minus min equals 2400. When I add these up, I have 2 max plus no mins equals 20,400. So that means the max is half of that, which is 10,400. 10,200. And if the max is 10,200, and I know that the difference between the max and the min is 2,400, then all I have to do is subtract 2,400 from 10,200, and I get 7,800. And notice that means when I add 10,200 plus 7,800, I get 18,000. So there's my max population and my min population. Bam! Okay. Now, the last thing they ask us to do is graph this thing, and then we can answer some questions about it. So, let's make some room so we can graph. So we've got a period of 10 years. Notice we have no negative population and no negative time either. So 10 years, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Population. All right, I'm sorry, time. Now we have the maximum that we said was 10,200. So, well, let's do it like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so population in the thousands. So 1,000, 2,000, 3,000, 4,000, 5, 6, 7, 8, 9, 10, 11,000. Now, we know that the midline is 9,000. And we know that the upper line is 1,200 above that. And we know that the lower line is 1,200 below that. So that gives us our max and our min too. If you just go from 9,000 up 1,200, you have your max. You go from 9,000 down 1,200, and you have your min. Now, our box is 10 wide, and as always, we want to cut our box in quarters. So half of 10 is 5. Half of 5 is 2.5. So now we draw our curve. And this is a cosine curve, so it obviously has to be red. So we start at the top, middle, bottom, middle, top. Now, notice the only reason this is a different shape than what you see in the book on page 183 is because we just scaled it out differently than the way the book did. So the last thing they ask is, and estimate the number of years the population is less than 8,000. So if we take 8,000 and we'll just draw a line across here at 8,000. So the time that it's less than 8,000 is from 4 years to 7 years, which is 3 years. Let's see what the book, oh, see the book went from 4 to 6. Yeah, see, they're obviously messed up. No, I'm doing this freehand, so I'm probably the one that messed up. See, notice it is a little bit longer on the right than it is the left. So 4 to 6 does make more sense. So if you're doing an accurate graph, then you can answer questions pretty well with your graph. Okay, one more example. So on page 181, it's example 2, and this is really simple. What we see is a table of frequencies of different notes, and we have different octaves in the frequencies also. So now an A in the second octave would be 110 hertz. That's a low note. Now if you go an octave above that, you're at 220. You go an octave above that, you're at 440. So the higher the frequency, the higher the tone. And so now, you see the graph here. The x-axis is the time in milliseconds, 10 to the negative third. So let's take y sub 1, the pink graph, and it goes to 4 times 10 to the negative third seconds. So 4 times 10 to the negative third seconds per cycle. That's how long one cycle takes, is 4 to the negative third. Now, if I want the frequency of that, then I reciprocate this. So 1 over 4 times 10 to the negative 3 would be cycles per second. Now 1 over 4 times 10 to the negative 3 is 1 over, well, let's just do it like this. 1 over 4 thousandths, which equals 1,000 over 4, which equals 250. So the frequency of that first red curve is 250 cycles per second, 250 hertz. And so what we do is we look for the note that's closest to 250, and you see that ends up being a B in octave 3. B in octave 3. Okay, now let's look at the blue curve. Notice that goes to 6. One cycle is 6 to the negative times 10 to the negative 3. So 6 times 10 to the negative 3 seconds per cycle. So that means we've got 1 over 0.006 cycles per second. And that's my frequency. All right, so what is 1 over 0.006? That's 1 over 6 thousandths, so it's 1,000 divided by 6, which is, let's see, what's that, about 166.67? Yeah, 167 hertz. Okay, so we look at the note that's closest to 167 hertz, and notice it's the E in octave 2. That's it, piece of cake. Have fun with these.
That's all, folks.